Yes, welcome back. In the previous topic, we were discussing about the deflection of beam. So then we have discussed how we can able to identify the strength of the beam, then elastic line. Then we have discussed of flexural rigidity or a stiffness, more flexural rigidity. So like this. Now we're going to derive that how we can able to obtain the flexural rigidity. The product of Young's modulus and moment of inertia is used to denote that is the product of both of Young's modulus and moment of inertia is used to denote the that is what we call it as a flexural rigidity. Now we can able to see this flexural rigidity where in the diagram that is a theta plus d into theta, that is nothing but angle and the change of along with the change of angle. So when the change of angle comes into the picture, that is nothing but when the deflection comes into the picture, along with that the change of angle also will come with respect to the length, where you can able to see in this. So this is initially is that one particular, that is the axis. Whenever the load is applied, the deflection is formed, where you can able to see this is the axis line where the deflection is formed. Along with this, where you can able to see this is the x and y line, where from theta along with the deflection x plus dx and y plus dy, that is the change in length along with the x with respect to y at a point from a, that is where we consider point x and y at point c. So this is nothing but the angle of that is change in angle and the radius for that angle with respect to point o. This is what the diagram. Now let A be the part of the beam which is bent into the arc of the circle, where you can able to see that is the AB is then a part of the beam which is bent into an arc of a circle, and xy be the coordinates of A, and x plus dx and y plus dy be the coordinates of the B, and the length of the arc AB will be equal to ds, and let the tangents A and B make the angles Q and Q plus DQ with respect to x axis. Now when differentiating with respect to, where we can able to see that along with this coordinates, A will be the coordinates of x and y, and the B is nothing but x plus dx and y plus dy. This is the coordinates where we have seen in the equation. Now tangents, that is A and B, that is angle, it makes an angle that is theta plus d theta with respect to x axis. Now when you differentiate both the sides along with the with respect of x, so what happens when you differentiate along with x, we're going to when we differentiate with respect to x, so it will become d theta by dx, that is secant square theta will be into d theta by dx. Now we differentiate with this term, what I'm going to get is nothing but d square y by dx square. Secant square theta into d theta by d theta by ds, that will be equal to ds by dx will be equal to d square y by dx square. So when I'm going to differentiate with respect to x and y, this is what I'm going to get, that is equation 1. We have from figure, what is that, from the diagram, ds will be equal to r into d theta, where d theta by ds will be equal to 1 by r. From triangle ABC, when I am considering, or when we consider the triangle ABC, what happens, ds by dx will be equal to secant theta. So from equation 1, what the equation 1 we got is nothing but secant square theta into d theta by ds, that is the ds by dx will be equal to d square y by dx square. Again from triangle ABC, ds by dx will equal to secant theta. From equation 1, d square y by dx square will be equal to secant square theta, that is into 1 by r into secant theta. Now 1 by r will be equal to d square y by dx square by, when I'm differentiate and I'm taking this term outside, now I'm differentiating with this both these terms. 1 by r will be equal to d square y by dx square by secant square theta into secant theta. We brought this term to the down. Now when I substitute this, what happens, d square y by dx square will be secant square theta into secant theta. What happens, when I'm differentiate, the formula will become as, or the equation will become 1 plus tan square theta into tan square theta into 3 by 2. So when this equation we're going to get, that is when I'm going to differentiate with the secant square theta into secant theta. Now what happens when we find out for the deflection of the beams? So what happens when you find the deflection of beams? Now the it becomes the 1 by r, 1 by r into, that is 1 by r will be equal to d square y by dx square. d square y by dx square when I differentiate the tan theta 1 plus dy by dx whole square into 3 by 2. Since dy by dx is small, its square is still small, so we are neglecting the dy by dx square because it is very small. So now we have 1 by r will be equal to d square y by dx square. Now from bending theory, already we have an equation bending theory, that is m by I will be equal to E by R. So from the bending theory, what we are going to obtain now is m, when I cross multiply this, so m into E by m by E into I, that is will be equal to 1 by R. Now I'm again, if I multiply this, m by I will be equal to, what is the 1 by R value, will be 1 by R is equal to d square y by dx square. So this is the what the 1 by R. Now when I substitute this m by E into I, that will be equal to d square d to the power of 4 by y by dx square. When that is, when I substitute d square y, this is the value of 1 by R. Now the equation will become, now if I multiply this, so m will be equal to E into I d square y by dx square. So this is the what the final equation we are going to get, that is to find out the deflection in the beam. So m will be equal to E into I by d square y by dx square. So where this we can able to see this from, we got this equation from the flexural rigidity. The flexural rigidity is nothing but an product of Young's modulus and the moment of inertia. So this is by using this only we can able to, or we have find out at the bending equation. So by substituting all these terms, by taking the coordinates from A, B and C along with the tangents A and B, when we reach the angles make, that is q theta plus d theta, so we got the substitution. So finally when we are neglected here the dy by dx, because it is very small, angle is very small, that is dy by dx square, so we have neglected. So now when finally we are going to substitute what the equation what we got is nothing but an m will be equal to E into I by d square y by dx square. So this is the what we are going to get the, or what is the equation to find out the deflection in the beams. So in this shear force and then a bending moment and bending stresses and the deflection of beams, so these are the things that what we are going to learn along with the numericals. So the numericals might be for all the different types of bending stresses and different types of beams along with the loads. So as I told, point load, UDL load, UVL load for a simply supported beam or in a cantilever beam or in a uniformly varying load, all these beams we are going to solve the problems along with this, and we are going to solve the problems for the deflection in the beams, how to find out the deflection or how to find out the flexural rigidity, how to find out the strength, stiffness, like this. Then we are going to find out the bending stresses, whether it might be in a compressive stress or whether it might be in a tensile stress. For in a different beams we are going to identify the different types of stresses along with this deflections and then a bending stresses along with the different types of beams. So these are the things that what we're going to learn in the module 3, that is the shear force, bending moment and the bending stresses, right? So this is what we're going to completely study along with the problems. Thank you.